From setting out in late 2008 exploring topics of low energy retrofit to today, the long journey of research has been tumultuous. At the outset, I packed my baggage of opinion and bias. As co commentators on my travels and travails, we would encounter the low gullies and high cliffs of contradiction and affirmation. It became clear to me that an invisible potential may be buried or concealed in my research building. Hypothetically, this potentiality could impact design decisions for artifact retrofit and outcomes of the research. I first faced the question of why do we constantly replace buildings without studying the potential for their reuse. This question of retrofit and reuse in the design process seemed to be less measured and less involved than new build. However, in the context of energy, each existing building represents an investment or cost in embodied, operational, and end of life energy. The focus of my research would be the regional technical colleges. To consider retrofit methodologies, we had to elicit their potentiality. I soon discovered that my friend's opinion and bias had to be ejected from the research bus and left at the curb. I had to rebuild a picture of the forces that shaped the design and construction of the regional technical colleges in order to both discover the new potentialities and value the existing structure. The socio-political environment may have impacted the architectural intent of the building. 1960s Ireland was a much different place, where social inequity was underlined by massive disparities in third level access. With a low level of technical graduates threatening a fledgling economic revival, this influenced the government plans to establish a technical education sector. The political and physical response was uniquely expedient and opportunistic, but compromised in haste and expenditure. The resultant architecturally brutalist buildings were inadequately equipped to cope with the post-oil crisis world, like many of its precedents. The architectural language and technologies that would inform the RTCs can trace their origins back to the turn of the 20th century, where a maelstrom of change was in the air of society. At the height of the Art Nouveau movement, some architects were seeking a more honest and less embellished direction to inform the future of architecture. As Art Nouveau was in its prime, a few scholars like Hermann Matthäus argued against the extravagances and over-decoration in favour of a more rational and utilitarian approach. This was called New Objectivity. Soon after, he would set up the Deutsche Werkbund, where, amongst others, Peter Behrens, a prominent German architect in the Art Nouveau movement, would design the AEG turbine factory in Berlin in 1909 in the style of industrial classicism. Behrens' subsequent design language would influence his assistants Adolf Meyer and Walter Gropius. The Gropius-Meyer Fagus building of 1911 to 13, which would be christened the first modernist building, bore striking resemblances to the AEG precedent, in a regular fenestrated grid laid out in vertical panels, but with less relief. The image across illustrates a lot of curtains inside the glass of the top floor, boxes and awnings on the mid-floor, and obscured glass on the bottom floor, which might evidence overheating or a poor consideration for heat gain by Gropius and Meyer. The technical understanding of heat gain or of building physics may have been absent from their experience or education to date. However, we would assume that they would learn from it. In 1914, Matthäus maintained that the industrial technology enables standardization or type, which would result in universally valid forms. Combined with Sant'Elia's concept of brutalism in architecture, with the use of concrete, steel and glass to be ugly in its mechanical simplicity, we start to see the emergence of style of functionalism and early hints of brutalist thought. By the time Gropius completed Dessau Bauhaus in 1926, from a reinforced concrete frame in a grid structure, we might expect to see a greater understanding of heat gain from a greater level of experience. However, Sennett offers that the building suffered from problems of poor insulation, undersized and inefficient heating systems, high heat gain and heat loss from the expansive unprotected and non-insulated glass facades, and poorly maintained roofs, which led to leakage. The architecture of Dessau Bauhaus may justifiably be celebrated in modernism for aesthetic form, open space and light, but in its technical environmental rigour it can be called into question. Gropius left the Bauhaus to be replaced by Meyer and later by Mies van der Rohe. Gropius quit the Bauhaus for London in the early 1930s, where a new national plan for Britain favoured his more modern approach. Gropius and Fry were employed by its author to design the new town of Histon Village and its senior school, Impington, development in 1936. Their modern design was at variance from contemporaries like the New Bodleian Library by Gilbert Scott. It established basic standards for room size, light, and ventilation that we still employ today. Its master planning offered proximity to the workplace, grocery stores, and childcare. The prefabricated finger planning for the schools became a template for British school design after the war. Gropius had argued only perfect harmony in its technical functions as well as its proportions can result in beauty. Good architecture should be a projection of life itself and implies an intimate knowledge of biological, social, technical, and artistic problems. Here, again, we would assume that Gropius had learned from previous environmental planning problems. Early sketches illustrate overhangs at the entrance building, but the finger classrooms had minimal overhangs and large expanses of glazing. There exists evidence of some progress here. Mies van der Rohe was forced to close the Bauhaus in 1933 by the Nazis and emigrated to Chicago in 1938 to become director of Illinois Institute of Technology. His first building, the Armor Research Foundation Metals Building, seemed to be a development of his 1935 Versteg factory in Krefeld, Germany, and similar in style to Gropius's Fagus Works building 20 years earlier. He would continue to develop the style heavily expressed geometry emphasized by black framing, cream brick, and glass. His 1946 Wisnik Hall would greatly influence Michael Scott's facade of the 1967 Regional Technical College buildings in Ireland, with its reinforcement of the 24-foot by 24-foot room plan. Although Hawkes would argue that Mies's Tugendhout house of 1930 was environmentally advanced, Wisnik's flat facade lacked relief, and large glazed sections did little to avoid heat gain and heat loss, although significant shading is afforded by the deciduous trees on its perimeter. Post-war London saw the development of the new towns, and G.C. Stillman pioneered non-traditional steel grid structures for primary and secondary education, based on 3 bay modules of 24-foot by 24-foot classrooms. Prefabricated steel structures with external cladding or infill panels resulted in a very fast construction pace, which was considered very successful by London City Council. The external horizontal precast concrete infill panels replaced the traditional brick. The aesthetic was particularly brutal and ugly, but effective, modular, and fast. The new Labour government faced a lack of traditional materials and skills, and urgent needs of post-war rehousing and education, thus prioritised speed of construction over cost. The subsequent British government cut educational spending by a third in 1951, prompting an analysis of materials and construction techniques. The separate elements of a building, the foundations, steelwork, cladding and roofing, were priced independently. The Hertfordshire light steel frame cost approximately £3.5 million for a typical construction. An equivalent school constructed from concrete frame cost approximately £1 million, and a traditional load-bearing method of brick, still in short supply, cost £0.5 million. The clear advantages of the industrialised system came in its speed of construction over the traditional methods, but at 7 times its cost. Before the Conservative government budget cuts of 1951, the Smithsons had started construction of Hunstanton School in 1949, which was heavily influenced by Mies van der Rohe's Chicago IIT buildings, which had featured in the Architectural Review of 1946. Where Mies's work at IIT was refined and taught, the Smithsons' work at Hunstanton was raw and brutal. The construction was express with each exposed weld, bolt and pipe. Hunstanton is more honest than Mies's work. What you see is a true structural frame, welded on site to make a continuous plastic structure, to save steel. The standard sections, though large and in short supply, were relatively cheap. The brick end walls braced the structure, and inside the finishes and pipes are all exposed. The building would seem to continue an architectural emphasis on the proportional grammar over technical performance. Shorten declared to the Times that on Stanton was a tragedy. He complained about water ingress, the lack of expansion joints, cracking windows, and expanding metal frames. This building's principal problem was that it was freezing in winter and too hot in summer. In 1963, Arup Associates, a collaborative multidisciplinary practice, was formed under principles of total architecture. Their first project, the Mining and Metallurgy Building at the University of Birmingham, was designed by architect Philip Dowson, with particular attention to adaptability and servicing. The project was designed around 5 interlinking pavilions, as space defining rather than object. Each pavilion was based structurally on a tartan grid with extensive prefabrication of concrete elements. MacDonald argues that Dowson consciously used concrete to moderate internal thermal environments to shift the diurnal cycle of heating and cooling. The project, completed in 1965, went on to win plaudits for their clarity, logic, and elegance, winning the 1966 REBA Architecture Award for the West Midlands. The highly glazed facades had little in the way of shading. The concrete structure was expressed, but have a thermal mass functionality and would prove more durable than its steel predecessors. The template would directly inform the design of the RTCs in Ireland, as Arup were common to both design teams. In the mid-1960s, Ireland was on an economic upswing, and the new Minister for Education, Donogh O'Malley, set about an ambitious building programme establishing regional technical colleges to address a massive social inequity whereby a child was 68 times more likely to go to college if they had upper-class parents than those of manual classes. The government, industry, and the World Bank all recognised that there was a massive gap in the education of technicians for industry, and this was becoming a serious threat to the potential for national economic growth. A change had to be made. Embracing the Misesian ethos, O'Malley structured education like an assembly line, delivering the children of the working classes to second and then third level education on a scale never seen before in Ireland. He grasped power from the local church-dominated vocational groups. Making an executive parliamentary decision, he announced his intention to set up the RTCs in 1966, quickly establishing a steering committee to inform the design brief. This move emasculated an existing Commission on Higher Education established by his predecessor, whose recommendations on a new third-level structure remained unpublished. In the existing regional appointments, O'Malley handpicked a team he wanted for the largest multi-site construction project in the history of the state, under the guidance of Desmond McCreevy, a close friend of O'Malley's and political party chief fundraiser. The new design team was formed by a consortium called Building Design Associates and included people like Michael Scott, Arthur Gibney, J. Coleman Healy, Owen Kennedy, Arthur Main, and Arup's leading engineer in Ireland, Jock Harbison. The minister required a tight 3-year design and construction period starting in late 1966 and completing the first phase of 5 buildings by September 1969, with a 20% cost and time savings over traditional methods, which would seem to contradict existing systems and cost knowledge from the UK. Faced with such a plain-speaking, unwavering client and impending deadlines, the design team research trips were delimited to London City Council and Birmingham University. The trip may have been informed by Irish architect John Burgess, a member of the team who had worked in London on new towns, and of course Arup Associates, who had worked on the M&M building. Expeditiously, BDA adopted the tartan precast reinforced concrete frame and 24-foot module for the RTCs, and combined it with a more cost-effective prefabricated concrete cladding system which effectively concealed the structural grid. The initial design proposed by BDA in March 1967 had less than 5 months for design and research. It was budgeted and presented to Parliament at a cost of £7.2 million sterling for 9 college campuses, for which further savings of 16.4% were demanded by the Oireachtas. The original design lacked relief, and depended on material quality on the interior. The precedent baseline interior of parquet floors and cream brick walls was replaced with poorly fabricated fair-faced concrete block and linoleum flooring. Equipping budgets were all cut back, and independent columns would now be cast together for efficiency, abandoning one of Dawson's servicing objectives. The resulting design, which differed in outward aesthetic, quality finish, and firmness from its UK precedent, progressed apace to site with different project teams. A unilateral decision made by the minister had resulted in a single concept design team for all 9 sites, and then the political backlash resulted in different project teams for the same sites. The lack of continuity between the design and construction teams may have separated the implementation from the ethos of the precedent template. A lack of design and fabrication experience in industrialized prefabricated buildings may excuse the poor workmanship and finish evident from the concrete casting and block walls of the RTC. The regional technical colleges completed between 1970 to the close of 1974, in the midst of the first oil crisis. On the opening of the last building, a newspaper reported that the structure and design of the building had created many problems, such as the heating. As the building is not insulated, the heat disappears quickly. The large expanse of glass and bare block add to the coldness of the structure, which is ugly to the eye. The double-loaded corridors and limited natural ventilation was not fit for purpose from the outset. The lack of shading and expansive glazing caused a lot of heat gain and heat loss. Massive internal summer overheating, often 36 degrees, with a lack of assisted ventilation, create oppressively inhumane working environments. The inadequate central heating system never reaches minimum thermal comfort levels in the winter. The highly air permeable envelope caused fast heat loss but did mitigate CO2 buildup. As a result, the thermal mass cools quickly and prevents the building from achieving adequate thermal comfort levels in winter. Part project funder, the World Bank, conceded in the wake of the second oil crisis that the design had serious faults, particularly with regard to high energy consumption. Basically, there had been an inadequate cost provision to meet environmental, heating and ventilation engineering needs. A design with a high percentage of single glazed windows, inadequate roof insulation and no thermal control have cost high costs in use, exacerbated by the international energy crisis. In 1967, the Cork RTC budget was £1.45 million, which more than doubled to an eventual cost of £3.2 million. Successor to the RTC typology, the steel clasp industrialized systems suffer from rust to structural members, limiting their practicality for retrofit. The precast concrete RTC typology suffer from delaminated cladding, deteriorating seals, poor airtightness, high surface condensation, and high energy costs. However, the main concrete structures suit flexible internal replanning and adoption to a mixed mode, highly insulated building with natural ventilation and the use of exposed thermal mass to achieve low energy performance, improved indoor air quality, and thermal comfort. The utility of what we call modernist, functionalist, and brutalist architecture is compromised by an overemphasis on geometric form over technical function. Despite the internationalist aspirations to technical rigor in their commercial buildings, the performance of these buildings tell a different story. Buildings like Mises IIT campus, the Smithson's Hut Stanton, and Dowson's M&M building all have beauty in their functionalism or brutalism, but all suffer from compromised environmental performance due to an emphasis on style. Gropius had warned on a trip to UCD in 1936 that the imitation of modernism would be distorted by political misadventure, and such a distortion would result in the inadvertent loss of the truth and simplicity of modernism. The concealment of the structural grid and the overemphasis on cost rationalization in many industrialized system builds of the 1960s led to a visual squalor, devoid of humanity, where the medium is the only message. In retrospect, it is sometimes difficult to perceive why buildings are the way they are. The fashion of brutalist and industrialized architecture were of the era and promised a more egalitarian world. But like all things, they can be easily corrupted by politics and myopic decision making. The lack of both architectural continuity and adequate time to properly detail the RTC design scheme meant that the largest multi site development in the history of the state became a cold and emotionless epitaph to a once colourful politician. The result is a cold and uninspiring space that has become a victim to politics and drudging. For all the haste and cutbacks, we've been left with a second class institution in second class accommodations, compromised by a political expediency, burdening all users with a legacy of greater cost and lesser utility. I will finish with Norman Foster. As an architect, you design for the present with an awareness for the past, for a future that is essentially unknown. Thank you. when his emphasis on proportion so outweighed the technical function of his buildings.